Checking. Checking. Okay, the audio works. And we're in. Let me just exit this. Now, this morning I am going to be looking at right triangle trigonometry, in particular evaluating trigonometric ratios, and I am to find the value of the trig function indicated. So, finding secant of theta in the right triangle whose legs are 8 and 15 and whose hypotenuse is 17. Finding secant of theta. There, when I said that the legs are 8 and 15, I should have said the opposite side is 8 and the adjacent side is 15, as these are relative terms. Okay, so the adjacent side to theta has a length of 15, and the opposite side to theta has a length of 8. And the hypotenuse, the longest side of the right-angled triangle, has a length of 17 in this particular case. But what is that function secant of theta in terms of something that we know? Secant of theta, by definition, is 1 over the cosine of theta. Okay? And the cosine of theta is, going by SOHCAHTOA, is, I'll just put that on the board as well, just as a reminder about what that is. So the right-angled functions that you already know are sine, cosine, and tangent. And that's the S, C, and T. And so SOHCAHTOA, Ka for cos, or cosine. And what this means is the cosine of theta equals the length of the adjacent side in the right-angled triangle divided by the length of the hypotenuse in the right-angled triangle. So, because secant of theta is 1 over cosine of theta, that means that secant of theta logically should be 1 divided by this. And when you do 1 divided by a fraction, you flip it. So this should be the hypotenuse of the right-angled triangle divided by the adjacent of the right-angled triangle. So in this case, secant of theta should be, in this particular case, it should be 17 over 15. Okay, let's see if that's correct. Scroll down a little bit, and bingo, 17 over 15. Or 1 and 2/15. 1 and 2/15 if you like. Great. So, what about secant of theta in this case? Secant of theta is the hypotenuse over the adjacent. So, we can just write that. It's always good to write that. The hypotenuse over the adjacent, which in this case is what? The hypotenuse is 13. That's the longest side, and we can tell because it's opposite the right angle. And it's because it's the biggest number as well. And the adjacent side is the one that's closest to or next to the angle. One of the shortest side that is closest to or next to the angle. So it would be 13 over 12. 13 over 12. Or 1 and 1/12. Okay. What about cot of theta? Cot of theta, also known as the cotangent of theta, is 1 over the tangent of theta. 1 over the tangent of theta. Let's write that down. Cotangent of theta is 1 over the tangent of theta. And the tangent of theta, going by SOHCAHTOA, is this one here. So it must be the opposite side divided by the adjacent side. And by the reasoning from before, that means that the cotangent of theta flips that. So it's the adjacent side over the opposite side. Okay. And what is the adjacent side to theta? It's 4. What is the opposite side to theta? It's 3. So the cotangent of theta, of the angle theta, is 4/3. 4/3. Just check and make sure that's right. And it is. Great. Next, CSC of theta. What on earth does that mean? That is the cosecant of theta. The cosecant of theta. Sometimes you will see it written like this, cosec theta, and usually it is read aloud as cosec theta, but the cosecant of theta, cosecant of theta. And the cosecant of theta is defined to be the sine of theta, 1 over the sine of theta. And again, using SOHCAHTOA, it's the SO in SOHCAHTOA, as this means sine. Sine of theta is the length of the opposite side divided by the. Therefore, cosecant of theta must be the length of the hypotenuse divided by the length of the opposite. So applied to this case, it must be 17 over 15, as 15 is opposite theta. We'll just check and make sure that's okay. Yes, it is. So that's all of the newer trig functions attended to: cosecant, secant, and cotangent. Now it's just getting used to them. It's just a case of getting used to them. So cosecant of theta, that's 1 over sine of theta. Sine of theta is opposite over hypotenuse, so you just flip it. So hypotenuse over opposite. Hypotenuse over opposite. Hypotenuse is 24. Opposite, the side opposite the angle, is 16 root 2. We simplify this because it's got 24 on the top, 16 on the bottom, so clearly multiples of 8. So we write 3 over 2 root 2. Then we go a little bit further. A little bit further? Why? Well, it's seen as not so great to have a square root sign on the bottom, to have like a surd on the bottom, if you can help it. So multiply the top and the bottom by the square root of 2. This is called rationalizing the denominator. That means that you will have 3 root 2 on the top, and then 2 root 2 times root 2. Well, root 2 times root 2 is 2, and 2 times 2 is 4. So 3 root 2 over 4. And I really do hope that they did that. And they did. Great. You see, it is sort of standard practice to do that. Okay, moving on ahead. Cosine of theta. Back to the standard trig functions, I see. Going by SOHCAHTOA, the cosine of theta is the adjacent side divided by the hypotenuse. What's the adjacent side to theta? Well, it's 14 root 2. What's the hypotenuse? Well, it's 21. So this is cancelling the 7, the common factor of 7 on the numerator and denominator. This is 2 root 2 over 3. Okay, cotangent of theta. Cotangent of theta is adjacent over opposite. So, what's the adjacent to theta? 20. What's the opposite to theta? 15. 20 over 15 simplified? 4 over 3. Simple. Tangent of theta is the opposite side divided by the adjacent side. Well, okay. In full, it's the length of the opposite side divided by the length of the adjacent side. Or for short, opposite over adjacent. Opposite over adjacent. So for theta here, that would be 22 over 2 root 3. 2 root 23. Cancel out the 2, so 11 over root 23. Multiply the top and bottom by root 23, aka rationalizing the denominator, and we have 11 root 23 over 23. Next, tan of theta. Tan of theta is opposite over adjacent. Opposite over adjacent. Opposite is 6, adjacent is 8, so it's 6 over 8, so it's 3 over 4. Cotangent of theta. Cotangent of theta. Cotangent of theta is adjacent over opposite, so that's 2 root 5 over 4. Adjacent over opposite. Cancel out the 2, so that's root 5 over 2. Tangent of theta, what's that? Well, that's opposite over adjacent. So that's 3 over 4, so 3/4. Cotangent of theta is adjacent over opposite. So what's that? That's 12 over 24, which is a half. Tangent of theta is opposite over adjacent. So 7 over 24. Sine of theta is opposite over hypotenuse. So 6 over 7. Now, using your calculator, because it's almost impossible to do all these in your head, find the value of each and round your answer to the nearest 10,000th. So, have a scientific calculator handy. If you don't, Google's just fine. The calculator built into Google. But if you use that, know that it's not in degree mode. Like if you type in cosine of 10 into Google, they don't know that you're working with degrees. So type in cosine of 10 degrees. Type that in. Okay, cosine of 10 to the nearest 10,000th. So I just type cos 10, and what do I get? I get a negative value. That's not correct. So that means that my calculator must be in radians. So I go Shift, Menu, I press 2 for angle unit. The menu is quite straightforward. I press 1 to enter degree mode, and then I press equals again. So cosine of 10 reads 0.9848. 0.9848. The digit immediately to the right of this 8 was a 0. This is called the decider digit. Right, so just a reminder about place value: tenths, hundredths, thousandths, 10,000ths. So we only go up to here, the 10,000th place. And this digit immediately to the right is called the decider digit. Decider digit. This sort of like rounding is just something that people kind of like they forget the details a little bit and they just kind of wing it, but that's fine. Anyway, sine of 60 degrees. This is a special one. This is known as an exact value. Exact value. It's one of the few results that you're actually expected to know. So, how many others are there? Well, 0 degrees and 90 degrees. Like, you're expected to know what sine of 0 degrees and sine of 90 degrees are. You have to just memorize it. You can figure out all sorts of ways in which it's logical, and there are many, but you do have to ultimately know this. Okay, then who else? Well, 45 degrees. I don't want to go into it now about why these values make sense, but just know that you have to know them. 30 degrees and 60 degrees are next. This one here is a half. This one here is root 3 over 2. So you could say root 3 over 2, and that is exact, but that's not to the nearest 10,000th. You need a calculator for that. Root 3 is 1.732. It pays to roughly know how big that is. Anyway, sine of 60. Type it in, I turn it to decimal, and I get 0.8660. 0.8660. So I do wavy equal sign, 0.8660. And yes, I do include that 0 at the end because they have asked for it to the nearest 10,000th, and I want them to know that I'm listening. Okay. Cosecant of 21 degrees. Cosecant of 21 degrees. That would be 1 divided by the sine of 21 degrees. Notice that there is no special cosecant button on your calculator because you are clearly quite able to just type in 1 on the top and sine of 21 degrees on the bottom, and we get 2.7904. 2.7904. Okay, I've noticed a small error up here. There should be a wavy equal sign, an approximate equal sign. Okay, so let's check and make sure that's correct. Great, 2.7904. Cosine of 60 degrees, another one that you're expected to know. Over here in the exact value table, I'm going to write down the results for cosine. And a lot of people remember this as simply like sine but going backwards. The exact values for sine but going backwards. And that's fine. Just for this small, very tiny portion of the table, that rule works. Okay? So therefore, it would be 1 root 3 over 2, root 2 over 2, 1 over 2, and 0. And that's fine. So cosine of 60 degrees is indeed exactly 1/2, which, to acknowledge their request, is 0.5000. Great. Tan of 40 degrees. Directly enter it into your calculator. Obtain the results, 0.8391 to the nearest 10,000th. Cosecant of 59 degrees, that's 1 over sine of 59 degrees. Enter into your calculator, 1 on the top, sine of 59 degrees on the bottom or the denominator, and we get 1.1666. 1.1666. Cosecant of 56 degrees is 1 over sine of 56 degrees. Enter into your calculator, 1 over sine of 56 degrees, and you obtain 1.2062. 1.2062. Great. Cotangent of 65 degrees. That's 1 over tangent of 65 degrees. So enter into your calculator. tan 65 degrees. And I'm going to hit the little reciprocal button, which is x to the minus 1 on many scientific calculators. Press equals, I get 0.4663. And we should check. Tangent of 10 degrees. Direct entry in the calculator. (0.1763). Tangent of 25 degrees. Another direct entry in the calculator. 0.4663. Did you notice how these are the same? Indeed, these are results that we'll start to illuminate more later. But it makes sense. Okay. So, before this point, I had some sort of audio troubles, like it wasn't picking up on my audio, or I was broadcasting a silent stream. So I'm just going to check and make sure that's not happening. Testing. Okay, it's totally fine. Going to resume the work. Find the value of the trig function indicated. Find cosecant of theta if tan of theta equals 3/4. Very well. Cosecant of theta is, let's see, cosecant of theta is 1 over sine of theta. And tangent of theta, well, let's see. That's the opposite side divided by the adjacent side. And sine of theta is opposite over hypotenuse. Therefore, cosecant of theta equals hypotenuse over opposite. So it seems as if we're stuck, right? We've got the opposite side. It must have a length of 3. But we don't have the hypotenuse side. So what do? We remember the Pythagorean theorem. In this case, it's particularly easy to recognize because of familiarity with the 3-4-5 triangle, that very special right-angled triangle whose legs have a length of 3 and 4 and whose hypotenuse has a length of 5. The very first triangle you'll probably meet for exposure to the Pythagorean theorem. So, cosecant theta must be 5 over 3. 5 over 3. And we'll just check and make sure that's right. Indeed, it's right. Okay. Find cotangent of theta if secant of theta equals 2. Secant of theta is 1 over cosine of theta. Cosine of theta, going by SOHCAHTOA, is adjacent over hypotenuse, and therefore secant over theta is a hypotenuse over adjacent. Cotangent of theta, remember TOA, is opposite over adjacent. So, beg your pardon, tangent of theta is opposite over adjacent. So cotangent of theta is adjacent over opposite. So, what do we do? These are kind of interesting. Secant of theta equals hypotenuse over adjacent, which is equal to 2. Maybe I'll put it as 2 over 1. So what we're going to draw the triangle. We're going to have theta there, the focus angle theta in the corner there. We're going to have the hypotenuse be 1 and the adjacent be, the hypotenuse be 2 and the adjacent be 1. And we want cotangent of theta, which is the adjacent divided by the opposite. So I think we just apply the Pythagorean theorem. The adjacent side is 1, relatively speaking, and the opposite side is 4 take 1 square rooted, so root 3, right? Yeah, that's right, and therefore this is 1 over root 3. Cotangent of theta must be 1 over root 3. And rationalizing the denominator, multiplying the top and the bottom by root 3, that must be root 3 over 3. We'll check and see if that's right. Oh, it is. Oh, wonderful. Okay, these are kind of interesting. I've never seen these problems before, although they're not too wild to think about. Let's try. Okay. Tangent of theta. I'm just going to immediately replace that with opposite over adjacent. Sine of theta. I'm going to immediately replace that with opposite over hypotenuse. Now the opposite divided by the hypotenuse is 4/5. So the adjacent must be 3 because this is clearly the 3, 4, 5 triangle. And therefore, for the opposite divided by the adjacent, that must be 4 over 3. That must be 4 over 3. I'm going to check these at each step. Yeah, that's right. Wonderful. Okay. Cotangent of theta is secant of theta equals 5 over 4. Cotangent of theta, I immediately replace it with adjacent over opposite. Secant of theta, that's 1 over cosine. So I remember k. So hypotenuse over adjacent. Hypotenuse over adjacent is 5 over 4. So this is the 3, 4, 5 triangle again, it appears. So this should simply be 4/3 for cotangent of theta. Oh, booyah, it's correct. Okay, so secant of theta. Well, that's 1 over cosine of theta. Cosine of theta is adjacent over hypotenuse. So hypotenuse over adjacent. That's what we want. And we have sine of theta, which is opposite over hypotenuse. So we shall place 13 on the top and then quickly apply the Pythagorean theorem. 13 squared, well, that's 169. 3 root 13 all squared is 9 times 13, which is 117. So we take that away and then we square root it, and then we'll get the missing side here. The adjacent side, beg your pardon. 169 take 117 appears to be 52. So root 52. So 2 root 13. Okay, wonderful. So hypotenuse on top, adjacent on the bottom, so 2 root 13 on the base. Then rationalizing the denominator, times in the top and bottom by root 13, and we get 13 root 13 over 26, so root 13 over 2. That appears to be correct. Excellent. Now, finding the cotangent of theta if sine of theta is 12 over 13. The cotangent of theta is the adjacent over the opposite, because the tangent of theta is the opposite over the adjacent, and it's the reciprocal. Sine of theta, going by SOHCAHTOA, is opposite over hypotenuse. So O over H is 12 over 13. And then a bell rings. Wait, I recognize this right-angled triangle. It's the special one, isn't it? The 12, 5, 13 one, isn't it? It is. 5 squared is 25, 12 squared is 144. Add them together, you get 169, which is, when you square root it, is 13. So that means the adjacent side is 5. So cotangent of theta is 5 over 12. Let's check if that's right. And it is. Wonderful. Okay. Next, draw a right triangle that has an angle with a tangent of 1. Tangent of 1. Okay. Tan of theta is the length of the opposite side divided by the length of the adjacent side in the right-angled triangle. So, what would it mean for the tangent of theta to be 1? That would mean that the opposite and adjacent have equal length. So, any right triangle will do, as long as the opposite and adjacent have equal length. So I don't know what this tool here does. Let's try and get it reasonably good looking. Something like that. Of course, if you had paper, ruler, protractor, or a set square, it would be a different story and different demands would be there. But for now, just do a simple sketch that looks reasonably okay. Never make your sketches deliberately bad. Okay, so theta is 45 degrees. That's how this happens. And opposite and adjacent have the same length. That's how you get the tangent of theta equal to 1. In problem 32, what is the slope of the hypotenuse for number 9? The slope of the hypotenuse for number 9. Okay, for number 9, the slope of the hypotenuse, we use rise over run. So the slope of the hypotenuse would be 3 over 4. And in comparison to the tan of theta, it's equal. Why? Because the tangent of theta is actually equal to the slope of the, when you do like an infinite straight line and you put a right triangle underneath it there, the gradient of this line is actually equal to the tangent of the angle of the line relative to the x-axis, going counterclockwise to the x-axis. Yeah, rise over run equals opposite over adjacent. Okay, wonderful. So all these were successfully handled, and now we'll move on. Where to next? We're going to be having a look at right triangles, where we have to find the measure of each angle indicated rounding to the nearest 10,000th. To the nearest 10th, beg your pardon. So, due to total paranoia, I'm going to check and make sure that the audio is still running. Just have to do this. Testing. Okay, still works. No worries. Find the measure of each angle indicated. Find the measure of each angle indicated round to the nearest 10th. Okay. Using the Pythagorean theorem and the well-known Pythagorean triples, which are like the special triangles which have whole numbers for the lengths of the sides, the special right angle triangles with whole numbers for the lengths of the sides, the ones that you must know are 3, 4, 5 and 12, 5, 13. So anyhow, to get theta, what do we do? Well, you know that, in this case, you can do almost anything that you want, right? I'm going to use tangent, the tangent function. So we know that the tangent of theta equals 5 over 12. Therefore, theta is the arctangent of 5 over 12, which to the nearest 10th we find on our calculator. So we press shift, then tan, and that gives us arctangent, which they denote as tan with a little tiny -1, which has absolutely nothing to do with being raised to the power of -1. Okay, so I type in arctan 5 over 12. I just literally write in 5 divided by 12, close it, and I get 22.6. 22.6. Okay, so on your calculator, it will almost definitely look like this. Tan, little tiny -1, 5 divided by 12, close brackets, hit enter, and you'll get 22.6 on your display to the nearest 10th. Let's make sure that's right, and it is. Wonderful. Let's move on. So, what about this triangle here? 13 squared at 4 squared, that's 169 at 16, that's 185. So this is the square root of it, 185. But no one asked us to actually find that out. So this is a little bit of extraneous work, extra work, unnecessary work. Let's find out theta using only the 13 and the 4. Using only the 13 and the 4. So I'm going to put a green around those and a red around this. This is correct, but it's not necessary. It's not necessary. Similarly, over here, I didn't actually have to find out that 5. I just knew it from memory. Okay? So, finding theta using only 13 and 4. Well, that means finding theta using only the adjacent and opposite side. So, we can use tangent of theta equals opposite divided by adjacent equals 4 over 13. So theta is the arctangent of 4/13. So you can write tan with a tiny little -1, but I really don't like it because it sort of gets people confused and makes them think that it's reciprocal of tan, which it isn't. So arctangent of 4/13, shift 4 divided by 13. We get 17.1 degrees, which looks right. Next, hypotenuse and adjacent. So, who's that? K. Cos theta is 6 over 9. Cos theta is 2/3. So theta is arc cosine of 2/3. Or about 48.2 degrees. Here, we have opposite and adjacent. So, use tangent of theta. Tangent of theta equals 11.9 over 10. So theta equals the arctangent of 11.9 over 10. Which, if you enter into your calculator, is 49.95958, which to the nearest tenth is 50.0. That's to the nearest tenth. And we check, and that's right. 50 degrees, although they didn't feel the need to do it to the nearest tenth. If someone asks you to do something to the nearest tenth, you do say that number, that numeral right there, 50.0 degrees. Next. We have opposite and adjacent, so we use TOA. So tan of theta equals 7.7 over 14. So theta equals arctangent of 7.7 over 14. $28.8. Adjacent, hypotenuse, K, theta equals arc cosine of 4 over 5. $36.9 degrees. Adjacent, hypotenuse, theta is arc cosine of 4.4 over 11. $66.4 degrees. Next, adjacent and opposite, but we recognize 3, 3. Oh, it must be the 45, 45, 90 triangle. So theta equals 45.0 degrees. In fact, that is exact. So, now what? Now we must find the measure of each side indicated. Find the length of each side indicated, find the measure of each side indicated, and we have to round it to the nearest tenth. So what do we do? Well, what's involved here? Let's just think about that. The adjacent and the hypotenuse, those are involved. And 37 degrees, that's theta. So we've got the ingredients, adjacent, hypotenuse, theta. Beg your pardon. What comes to mind? Ka. Sokatoa. Ka. C-A-H. C-A-H. Reminder, cosine of theta is the adjacent over the hypotenuse. So, cosine of 37 degrees equals 11 over x. So what's x? X is 11 over cosine of 37 degrees. And once you get up to speed, you'd be expected to be able to produce this just immediately or straight off the bat in one line, just like that. So 11 over cosine of 37 degrees to the nearest tenth is 13.8. And we check, and that's correct. Now, who's involved here? Adjacent and opposite. What comes to mind? Tan. So, tan of 32 is x over 13. So x is, beg your pardon, 13 tan of 32. Enter. We obtain 8.1. Next, adjacent, opposite, TOA, tan of 50.1 equals x over 5. So 5 tan 50.1 equals x. Type it in. Answer 6.0 to the nearest tenth. Looks about right. Who's involved? Adjacent, hypotenuse. So, Ka, cos of 60 equals x over 11. So x is 11 cosine 60. Cosine of 60 is an exact trig value. You're expected to know it. Cosine of 60 is in fact 1/2. That's exact. So it's 11 over 2, which is 5.5. Next, who's involved? Adjacent and opposite. So TOA, so tan of 41 is 4 over x. So x is 4 over tan 41. Approximate. 4.6. Next, who's involved? Opposite and hypotenuse. So sine of 57 is 10.8 over x. So x is 10.8 over sine of 57. or about 12.9. Who's involved? Opposite, hypotenuse, OH, SO, sine of 37 equals x over 10.3. So x equals 10.3 times sine of 37. About 6.2. Who's involved? Sorry, beg your pardon. Not sure what's going on here. Okay, great. So, adjacent, hypotenuse, cosine of 47 equals x over 3. So x equals 3 over cosine of 47. Or about 4.4. Now, new problems. Solve each triangle. Round answers to the nearest tenth. But are these really new? Well, apparently not. Apparently, the only thing that's new about them is that they invoke units. No problem. Another chance to get even better. But what do they mean by solve each triangle? Do they mean find all side lengths involved? Let's have a look. Ah, okay. Quite the demand. You have to find everything. Everything missing in every single triangle. That's what it means to solve a triangle. No problem. The internal angles of a triangle add up to 180 degrees, so 90, 62. So this must be 28 degrees over here. Then, then we can use whatever we want. So I'm going to use sine of theta. Sine of theta. So sine of 28 equals the opposite side. No, I'm not. No, yes, I am. Okay. Right. Be systematic. Cosine of 28 degrees equals 22.6 over the hypotenuse. So the hypotenuse must be 22.6 over cosine of 28. And we get 25.59. Now, we could use the Pythagorean theorem to get the missing side, right? But then we'd be feeding into it an inaccurate value. So why not just do it exactly? And it gives you more of a chance to practice the trig functions anyhow. Okay. So we use tan of theta then. Is that correct? Because tan of theta, that's the opposite side there. We're actually given the adjacent side, which we're to assume is as accurate as possible. Now, to actually get the marks here, because I noticed they've said round to the nearest tenth. So we'd say 25.6 miles. Now for the opposite side, we're given the adjacent and we want the opposite. So of course we use TOA. So tan of 28 degrees equals the opposite divided by 22.6. So 22.6 times tan of 28.6 times tan of 28 equals 12.0 miles. So that triangle there is solved. Indeed, there it is, completely solved. Okay, now to defeat all the others. 51 degrees there, so 39 degrees there. Correct. Okay. Okay, that has been complete. Moving on. Next, I will be investigating and trying to complete everything involved in this. But first, the customary paranoia check that the audio is actually being captured by something. Testing. And it is. So, back to work. Convert each degree measure into radians and each radian measure into degrees. Now, I should always have Miro open in the background, because a brief reminder about what radians and degrees are. Okay, while I'm doing this, I will say that degrees are a measure of the amount of turn. That's what they try to capture somehow. The sort of like measure of turn that seems to like be built into everything is turn itself. That if I do, 360 degrees, that's one whole turn. One whole turn. Okay? And then we come up with this idea called degrees. We have this idea called degrees, which is that we're going to say that one full turn is 360 degrees, a half turn is 180 degrees, and a quarter turn is 90 degrees, right? So, of course, turn is the more properly basic angle of unit of measurement for turn. So if I do 0 with a little t, and then half with a little t, and then 1 with a little t, 0 degrees, 180 degrees, 360 degrees. These are the more like appropriate units. Quarter turn is 90 degrees, and so on. And a 3/4 turn is 270 degrees. Okay? So, why 360? Why not 361? Why not 359? The answer is because 360 can be divided up into many ways. Think about it. The prime factorization of the number 360 is, well, let's see, 36 times 10. Then we break down 36. That's 4 times 9. So it's 2 squared times 3 squared times 2 times 5. Put that together, and we have 2 cubed times 3 squared times 5. Okay? And that has many factors. Its factors are 1, 2, 3, 4, 5, 6, not 7, 8, 9, 10. All the numbers from 1 to 10 except for 7. Incredible. Whereas 361 is only the product is 19 squared, and therefore it's only divisible by 19. 359. All right, let me think about that for a little bit. 3 obviously doesn't go into it, nor does not 5, not 7. What about 11? No, not 11. 13? No, not 13 either. 17. Not 17 either. 19? No. 23? No. 29. So I think 359 is a prime. Don't quote me on that though. Okay, so 360 degrees, the number 360 is justified, and we know what it means. We know what the idea is. What's a radian? A radian, first, just get up a simple diagram. Okay. When you construct a circle and you construct two line segments emanating from the center of the circle to the circumference of the circle, they're both each of them is a radius, so together they are radii, right? And they create an arc, a small arc on the circle. And when that arc has a length of the radius, that must be a very special sector indeed. That must be a very special sector indeed. So just to be clear here, I'll construct a circle, a crude approximation to a circle, because I'm not using a precise geometry package right now. There's the center by I. Again, it's just an approximation right now. There's a radius. There's another radius. And, you know, this thing here is a sector of the circle. It's a sector of the circle. And, beg your pardon, I meant to do that in black. When this arc here, this little arc here, has a length that is exactly equal to the radius. So for example, like you have a string and it's 5 centimeters long, you lay it end to end here, and it's 5 centimeters, a 5 centimeter radius, you lay it from there to there, and it's a 5 centimeter arc. That's a very special sector indeed. How much turn is that right there? Well, if you get your protractor, it appears to be around about 57 degrees-ish. 57 degrees-ish, right? And of course, it applies to any circle with a radius of any size because all circles are similar. So 57 degrees-ish. I should do a wavy approximation sign and then write 57 degrees there like that. Fine. So this amount of turn is known as a radian. A radian. Like that exact amount is known as 1 radian. 1 radian. Let's write that down. 1 radian is about 57 degrees. Okay. How many radians are there in 1 full turn? Well, 60 times 6 is 360 degrees. So is it like not a whole number? Absolutely. It's not a whole number. In fact, if you think about it a little bit, it must be 6 point something, right? And perhaps now you're willing to guess because pi is 3 point something. So is it like 2 pi radians to make 1 full turn? Correct. 2 pi radians equals 1 full turn, which equals 360 degrees. If you want the proof that 2 pi radians make 360 degrees, well, you know that the circumference of a circle is pi multiplied by the diameter. And the diameter, beg your pardon, that should be capital D. The diameter of a circle is half. That's not quite right. The diameter of a circle is the double of the radius. Okay, so okay, just give me a sec. So it's a question of like, how many radii does it take to make the circumference? That's really the question. So yeah, just replace D with 2r, so 2 pi r. And then there's your answer right there. It takes 2 pi multiplied by the length of the radius to create the entire circumference. And because a radian is like set up in such a way that that length there, that arc length there is exactly equal to the length of the radius, you can see how it makes sense. Now, let's put it in action. And let's solve. But just before that, a sip of water, why not? Convert each degree measure into radians and each radian measure into degrees. So if it said 360 degrees in question 1, we would reply with 2 pi radians. But it doesn't. It says 325. So what do we do? Well, if it said 180 degrees, I would have replied with pi radians. And if it said 270 degrees, I would have replied with 1.5 pi radians. So I'm noticing a pattern here. What you have to do is find out, is like, do this fraction here, 325 over 360, because that's what fraction of a full turn 325 degrees is. And then multiply that by 2 pi. And that gets you how many radians it is. Okay, so we could type in all of that on our calculator, but don't. Avoid that instinct. Instead, try to go as far as you can, just with your knowledge of numbers, and only at the very end approximate. Okay. So 325 over 360, what do they have in common? They have 5, the common factor of 5. So so 65 on top, 72 on the bottom, 65 over 36. That many radians, brackets, and a little tiny r up there. Let's see how true that is. Great. 65 pi over 36. Wonderful. Next up, 60 degrees, convert that to radians. Well, that is special because that's 1/6 of a full turn. So learn this. If it's 2 pi radians to make a full turn, then it would be 2 pi over 6, which is 1/3 of pi. Wait, where is my little tiny r symbol? Okay. Radians have such an important position and place in mathematics that they are often unitless. They often don't have a unit written down explicitly. And if you see a measure of turn in pure mathematics, you are to assume that it's radians once you get past a certain point. Okay. Negative 4/3 of pi. Negative degree? Negative measures of turn? Absolutely. Think about measuring the motion of a motor or part of a motor that turns. Wouldn't you want a way to distinguish between clockwise and anti-clockwise motion? Of course. So anyhow, we're going to just have a minus sign in front of whatever it is. So negative 4/3 of pi. Well, 1/3 of pi, as we've just seen, is 60 degrees. So 4/3 of pi would be 240 degrees. So this is negative 240 degrees. 23 pi over 12. Excuse me just a sec. I'm just trying to gather this up. If it said 24 pi over 12, that would be 360 degrees exactly. So we want to find 1/12 of pi is. 1/12 of pi is in degrees. So 180 degrees is pi. And 180 divided by 12 is 15. So it's 15 degrees less than 360 degrees. So that's 345. $570 degrees. 570 take 360 is 210 degrees. 210 degrees over 360 degrees is 7/12 of a full turn. 7/12 of a full turn is 7/12 of 2 pi. 7/12 of 2 pi is 14/12 of pi, which is 7/6. So 1/76. So 13/6 pi, I believe. Let's check. They say 19/6. Okay, well that's then. Oh, I see what my error is. 2 pi is 12, and 12 odd 7 is 19. Okay, fine. Okay. It's important to check. It's important to check. Okay. Now, negative 315 degrees. So that's 45 degrees less than a full turn, going clockwise, because anti-clockwise is the default for a positive degree measurement. 315 degrees clockwise. 45 degrees less than a full turn clockwise. 45 degrees is special. That's 1/8 of a full turn, which is pi over 4. So 2 pi take pi over 4 is 1 3/4 of pi, which is 7/4 pi. So negative 7/4 pi. And check. Correct. Now, convert each decimal degree measure into degrees, minutes, seconds, and each degrees, minutes, seconds into decimal degrees. Okay. I have no idea what this means. Okay, I'm going to guess if memory serves me correctly, 60 is an incredibly useful number because it's highly divisible. It's divisible by 1, 2, 3, 4, 5, 6, and so on. Okay. In fact, let's do the full thing. 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. Great. Highly divisible number, many, many factors. So in olden times, or perhaps still today, then, if it's featured here, they divided a single degree up into 60 minutes and a single minute into 60 seconds. And so this would be, so really we just have to worry about the 0.77 degrees, right? Like how many minutes is that? Okay, so 77 out of 100, we have to, best as we can, make that have a denominator of 60. "77 parts out of 100 is how many parts of 60? So what you do is you just do 77 times 60 and then divide that by 100. So 77 times 60 is 462, and 462, no, 4,620, and 4,620 divided by 100 is 46.2. So it's that much. Now, that is, so we can say, for example, that this is 128 degrees, 46 minutes, with a little prime mark or speech mark there, just like that. Single quotation mark, rather. And now we need to figure out how many seconds. Okay, so 0.2 is like the remaining bit here. And okay, 0.2. Well, that's a fifth, isn't it? Right. So that's a fifth of an entire minute, right? So that should be 12 seconds, shouldn't it? Something I haven't done before. It's the first time for everything, though. Let's see. Okay, bingo. That's actually right. Okay, this is better than I thought. 128 degrees, 46 minutes, 12 seconds. Okay. 232 degrees, 7 minutes, 57 seconds, converted to degrees. Okay. You add 7 over 60, and then you add 57 over 3,600. That's what I think you do. Now, so that's like 477, and so that's that. And I don't know. So I'm going to see. Plus. Okay, so I get 232.015. 0.016. But I'm going to say. Okay, totally wrong. Need to learn how to do this. All right, so Perhaps I just added up those fractions wrong. That's a possibility. We're only human after all. 232 plus 7 on top, 60 on the base, plus 57 over 3,600 creates this. So I evidently did that wrong. No problem. I just have to learn how to do it right. So 232.1325. That's what they say. But is that right now? Okay. Good. We have it. Now, how about this? Okay, the minus sign in the front. Just stick a minus sign there. We just changed the pieces up there. 42 where the 57 is. And 47 where the 7 is. And of course, 154 where the 232 is. And we get negative 154.795 degrees. Great. Now, converting this into minutes and seconds. Okay, this is going to be difficult. Maybe. All right. Okay, 92.25. Over 100 equals something over 60. Okay, 60 times 92.25, and then divide all of that by 100, and we get 55.35. Okay, so negative 0 degrees, 55 minutes, and 0.35 is the sort of like decimal part here. So $35 over 100 equals whatever over 60. So you have to do 60 times 35 and then divide all of that by 100, and that's 21. So I believe that it is negative 0 degrees, 55 minutes, and 21 seconds. Correct. Now, we have to find the measure of each angle. Okay, so I believe that represents a 350 degree angle. I believe, but let's check. And it does, because we go around counterclockwise or anti-clockwise, however you term it. Right, next up, this here, because a half turn is pi radians. And this is pi over 6, or pi by 6, as some people say. So pi take pi over 6 is 5 pi over 6. This here will be negative because we're going around clockwise. That's 20 degrees there. So 270 take 20 degrees is that. So it should be negative 250 degrees. Next up, we've done a full turn. So that's 2 pi. Then plus this little bit here. So half a turn is pi. Quarter turn is pi over 2. This here is pi over 3. Pi over 2 take pi over 3 is pi over 6. So it should be 2 negative 2 pi at pi over 6, so 2 1/6 pi. Or, if you want it as a full thing, negative 13 over 6 pi. Okay, top heavy. Now here, first, we're going around anti-clockwise, so it'll be positive. So, full turn, so 4 pi plus pi over 2, and then whatever the difference here is, so a quarter turn is pi over 4. This is 5 pi over 12, so that's 1/12 of pi right there. Put them together. That would be 7 pi over 12. So 55 pi over 12. Great. That represents a 370-degree turn. Draw an angle with the given measure in its standard position. Okay. So, obviously, I can't do that on here because I don't have a protractor. And there doesn't appear to be one that's like built in. So, I'm just going to approximate just for now. 280 degrees. It'll look something like this. $710 degrees. Okay, well, 720 degrees is 2 full turns, so 1 full turn. And just before you get to 2 full turns, a little bit under. Arrowhead there, 10 degrees there. Negative 120 degrees. Okay, so that'll be going clockwise, and it'll be a third of a turn. So, that's wrong. It should be like that. There, like that. 11 pi over 6. Well, 12 pi over 6 represents 2 pi, which is a full turn. So, there. Negative 10 pi over 3. So, that's 3 1/3 pi going clockwise. So 2 pi is a full turn. So here we go. 1 full turn. Then 1 1/3 pi. So 1 full turn, 1 1/2 full turns. And then a third of pi. And a third of pi is a 60-degree angle. So that should look something like that. And there we go. And whatever that measurement there is. Okay, I'm just getting a little bit fatigued now. Just give me a second. Three 1/3. Okay, 1 full turn, 2, 1, 90 degrees. Third, 60 degrees, 60 degrees, take that away. That should be 30 degrees. Fine. Okay, then 440 degrees. Okay, anti-clockwise. Anti-clockwise, and then 80 degrees. So one full turn. In which the terminal side of each angle lies. Okay, so don't really understand that question. I don't really understand that question, but I'll try my best. Okay, so first, a word about quadrants. Here on the XY plane, this is the first quadrant, second, third, and fourth, and they are indeed denoted by Roman numerals, capitalized. So, negative 509 degrees means that it's going to go clockwise, and it's going to be 360 degrees as a full turn, and then 360, 450. So then it'll be, there's 450. Then if we add on 90, we get to 540. We don't want to add on 90. So it's going to be in the third quadrant, I believe. I believe it will be in the third quadrant. But we'll have to check. Okay, affirmative. It's right. Next up. Negative 5 pi over 6. All right. That means we go around clockwise. 2 pi radians is a full turn. So negative 5 pi over 6 is nearly, well, that's, okay. So that'll be here in the third quadrant as well, I believe. It'll be in the third quadrant as well, I believe. But I don't quite fully understand this question. Okay, I got it. It's fine. All right, so that was all handled great. Mandatory paranoia check. Have to see if it's actually streaming the audio, and then I'll be back later to handle more. Check. Okay. So it works, and that ends the stream. If I can actually end it. 3, 2, 1.